Okay. All right. Let's do this. Welcome. Okay. Welcome back from spring break. I hope everybody had a good 9 days off and was able to rest and relax and not overly refresh your grade screen or whatever. Anyway, I'm excited to be back. And anyway, it's spring quarter. Who's graduating at the end of this quarter? Yeah, all right, a lot of you. Okay, so that's exciting, and congratulations to all of you for getting this far. And of course, more congratulations will be due in about 10 weeks. But yeah, looking forward to that. Okay. I thought I would just spend a little bit of time taking a look at the syllabus, which is here, and every quarter I take what I've learned from the previous quarter, and my syllabus gets longer. And so I remember my very first quarter I taught, my syllabus was 2 pages long, and now it is 7 or 8. I don't. It's a lot longer than it used to be as I keep adding stuff to it. But anyway, just a few things. This is how we'll do the grading breakdown. This seems to be the #1 question I get regarding the syllabus. So we've got homework, midterms, final exam. I'm not doing Piazza. I'm doing Campus Wire, and then we'll have class attendance and free points for being awesome, which I think all of you guys are awesome for just being here, so you get something for that, okay? Letter grades, straight scale, no curves, and it goes like this, okay? I usually aim for the exams to have a median of at least 80, and if the median comes in below that, I'll make adjustments accordingly, but if the median ends up higher than 80, then I feel like then we're okay. It must have been. I feel like it was a fair exam. So, okay. I think most of you have had me as a teacher before. Is anyone like this is your first time I'm your teacher? Okay, like 2 of you. All right. Anyway, my homeworks are coding heavy. I think that's like the #1 thing that people didn't like was that the homeworks were hard, but they'll be hard this quarter as well. My hope is that the homeworks are educational in value, and that by doing them you'll learn something. And learning is hard. That's the bottom line. Okay, it's hard for your brain to expand and incorporate new information and learn it. And that's so. If the homeworks are hard, I think that's a good thing, because that means I think you're learning. So because learning itself is a hard process. Okay. Anyway, don't submit your RMD files. Submit your HTML files. Make sure the requested output is visible in the homework. Okay, that's it's covered in the syllabus, but make sure that if it says produce this, it's produced. Okay. Late policies for the homework: 10-minute grace period, 5-point deduction for each hour it's late, but then the deductions stop at midnight, and then and that way you can get sleep, because that is very important. And then they'll resume at 6 o'clock the following day. And then if you need an extension, include your documentation with the homework. You don't need to send me a separate email or anything like that. Just include it in there. And then as the grader goes through, they'll grant you an extension as necessary. If you need something longer than 3 days, then come see me in person. Okay. And it can be retroactive. Like if you travel, like if there's an emergency and you travel out of the country and seeing me in person is not possible or something, just come see me when everything's finished. We can work something out, okay? All right, you have to buy a textbook for this class, okay? I generally try to avoid making students purchase and spend money on a textbook, but I couldn't find a textbook that I liked enough to use that was free, and so I ultimately picked this one. It's around 70, 80 bucks, okay? I know. And so if you want a legal version, you have to go to the bookstore and pay for it, okay? I might use excerpts from other texts, okay? Because there's a variety of stuff that I like to cover in a little bit more depth and some stuff that's not even mentioned in the textbook that we'll spend some time on. And so, you know, if I use those, I'll make sure to get ones that are freely available. But anyway, this is a text. I think it's really good. One thing I really like about it is, in my opinion, it is, and of course my opinion might not be right, but I think it's accessible for upper division undergraduate students, okay? A lot of other textbooks that get into machine learning type stuff is taught at in my opinion, you know, graduate level thing. So, but it gets into it, and I like it. So, okay, I'm going to be using CampusWire instead of Piazza. This is my first time trying it out. The actual people from CampusWire came and visited me and said, we want you to try it out. It's like Piazza, but better, is what they told me. I don't know if you guys have used CampusWire, and maybe your opinions are different on the thing, or you've never used it. But anyway, we're going to try it out. They said some issues that Piazza has that they've tried to handle in CampusWire is things like, I guess when you start asking a question, it will automatically search the other questions, so that, like, if the title of your question is similar to someone else's, like, it'll at least suggest those and say maybe it's already been answered. So we avoid duplicate questions. You get I forget what else. Oh, you get more points for answering questions, okay? And you get additional points if somebody upvotes your answer, okay? And so hopefully that will encourage good answers and good things like that, okay? This is important. Make sure that when you register for CampusWire that you use the first name and last name that appears in the roster. And if you have a preferred name, include that also, okay? So just, you know, put your first name, preferred name, first name, or whatever. Put both of those names in the first name field, okay? Because CampusWire is done by CampusWire, and so when I enter the grades, I have to kind of manually match them. And you know, if your name's, I can't match a name, it's hard for me, okay? More details in the syllabus regarding how we're going to do the CampusWire grading. 3 percentage points total. CampusWire has kind of like a, not a karma, but a reputation score, okay, based on how many upvotes you receive and things like that. And so that's what you get, okay? Anyway, I think this is the link, and you join with that. Some of you have already joined, like 10% of you. Okay, and then just guidelines as before. You can post any code that I put in the lecture, but don't post code that's your homework solution. Okay, I'm okay with like 1 or 2 lines of code, but not like your entire homework solution. Okay, but you can always suggest and say, try using this function. Try structuring your code this way. Okay, that I'm totally fine with, but just putting a chunk of code, not okay with that, all right? All right, I'm gonna do attendance. I like having you guys here. Attendance correlates with academic performance, and I only started doing attendance because earlier on, when I first started teaching, I didn't do attendance, and then by 10th week, I would be down to like 10% of the students coming, and and that was discouraging. And then the part that made me upset was that I would then get emails and questions about stuff that I said in lecture, and I feel like by having students come, we can avoid some of those issues. As usual, I'll do it via the online poll, and again, this part's important. Sometimes I'll do an actual roll call, not always, but sometimes. And if there's a mismatch between the actual roll call and the online poll, then the student will forfeit their attendance portion of the grade, okay? So just only respond to the poll if you're going to be here in class. Okay, you can work with others, but always write your own solutions. I don't want to see anything that looks like you copied and pasted from somebody else, okay? Don't copy someone else's solutions, and also don't post your solutions online. Okay, lots of resources for your well-being as a student, okay? I hope none of you face any kind of horrific or terrible circumstances this quarter, but sometimes life happens, and I don't want anybody to feel like they're alone. The university has resources, and I encourage you to make use of them. Okay, they're also listed off in the syllabus as well. Okay, I guess before we go on, are there any questions regarding syllabus-related stuff? We can also go through this. I don't know. Okay. I don't have control over this, but I want to say, let's make it a goal not to sit in the back 5 rows of the class, because I don't know, I walked up there, and maybe you have eagle vision, but it's pretty hard to see the screen, in my opinion. So we'll aim not to do that. Okay, but I don't know. Are you guys in the back able to read this up on the screen? This is the default text size. Okay, I switched over to. I'm still using R Markdown to make my slides, but I'm now rendering them as PDFs. That was people were complaining that they couldn't render their things as PDFs. So anyway, you get PDFs. It looks like this. I liked the other look, but here we go. Okay, and I can't really zoom in anymore. Okay. Anyway, this is Stats 102B, Computation and Optimization for Statistics. It covers a variety of computational algorithms that have important applications in statistics and machine learning. This course has existed as part of the statistics undergraduate curriculum for a long time, and it's gone through some slow evolutionary changes, and I feel like it's at a place that I'm pretty proud of. And so anyway, I hope you like the class. There's a lot of machine learning stuff are really just optimization problems, okay? They're really just optimization problems, which means all we're trying to do is trying to find something that will result in a maximum or minimum, or at least a local max or local min, okay? And okay, so this is a lot here, but this is some of the topics we will cover. So in the beginning, we'll spend a lot of time on just core foundational machine learning concepts, things like loss functions and likelihood functions, cross-validation, regularization. These are some key concepts that, I don't know, have you guys done machine learning stuff already or not really? Okay. I'm getting mostly slight shakes of the head, but thank you for that feedback. I much prefer shakes of the head than blank stares, which is also why I like having you here. Okay. All right, so we're going to look at some machine learning models, and we're going to start off with linear regression. And linear regression is, we don't often think of it as a machine learning model, but it counts, okay? And we're going to take a look at it from a machine learning perspective. We start there because I'm assuming you guys are already very familiar with linear regression. And so when I introduce these new concepts, I'm hoping it's not going to be overwhelming or anything like that. We'll also look at some neural networks, very basic neural networks, MLE for maximum likelihood estimation models, classification models, clustering, the expectation maximization or EM algorithm, and principal components analysis, PCA. Okay, and so we've got a variety of ML stuff going on. Some of you have taken 101C, some of you have not. And so this class overlaps with 101C, but there's a difference, okay, obviously. So in 101C, you learn even more kind of data mining, knowledge and data discovery and machine learning stuff, including the ones I listed, plus things like random forest and LDA, linear discriminant analysis, support vector machines, generalized additive models, I think, and their applications. While this course covers a lot of the underlying algorithms, the computational aspect that kind of drives those things, whereas I think, if my understanding of 101C is correct, that was mostly looking at this algorithm, this method exists, this model exists, and here's how we apply it, without learning the little kind of the gears and things that go on underneath, okay? And this one will kind of pull back the hood and you'll see the inner workings of some of these things, okay? So 101C focuses on the algorithms, and focus on the applications, and 102B focuses more on the algorithms themselves. All right, and so, and I like to kind of fit this in, a bigger picture of the stats major itself, just so that, I don't know, it feels like your education at least has some kind of flow to it rather than just being separate, discrete courses that have no connection to one another, okay? And so if we're just thinking of the stats major as a, kind of a whole, you've got stats 10, which kind of provides your foundations, introduces you to concepts of p-values and variation and things like that. And then stats 20 and 102A serve as like coding is important for statistics, okay? Because pretty much everything, like if you want to do any kind of job related to statistics, you're very likely going to have to write some code, okay? I guess it's possible that you can work as a data analyst somewhere using only Excel, but I would hope that you aspire for, greatness in that regard. Okay, but anyway, so you had stats 20, stats 102A, which kind of forms these computational foundations. The whole 100 series is all of the mathematical theory, right? Rather than just saying these things work, you actually had to derive them, and you go, okay, mathematically, they work, okay? And so, you have all of that, 100A, B, and C. And then, and this is my take on 101A and 101B, is that those are the statistical models that we can use when data is expensive, okay? So 101B is design of experiments, ANOVA, all of that stuff. And all of those methods were developed kind of during the 20th century by Fisher and Pearson and things like that, people like that, where collecting data required doing an experiment. Okay, you wanted to do something, you'd have to like plant seeds and grow them in the field and see how much they grew. Do you guys, right? You guys covered the Latin square in 101B, and did they show the fields of grain? Okay, so it was stuff like that, right? And you'd have to wait an entire season to collect like 10 data points, right? And so you wanted to maximize the amount of information you got from every single observation, okay? And so we developed statistical models like ANOVA and things like that that maximize the information you can get from that, okay? Whereas 101C and this class 102B comes from are more modern, where we are now inundated with just a ton of data coming in, and we're trying to make sense out of these gigabytes of data. Okay, and so data is cheap. We've got large data sets. And maybe more so, prediction is a little bit more important than interpretability, okay? With linear regression models, you had very good interpretability, right? Every single coefficient corresponded to a variable itself in the data set, and you were able to say something like, if we change, variable 5 by 0.01, it's going to have this effect on the outcome, okay? And then 102C, we do Monte Carlo methods, which kind of incorporate Bayesian models. And Bayesian models is all about being able to incorporate prior beliefs, okay? Rather than just depending on the data alone all by itself, you can also say, this is kind of what I'm expecting before I even look at the data. And that comes into the picture, okay? I think I've shown you this diagram regarding data science, and so this is Drew Conway's Venn diagram regarding what data science is, and it's kind of the overlap of hacking skills or coding ability, math stats knowledge, and substantive expertise. Okay, and so the stats major can kind of give you, or is hoping to give you, the top two circles, okay? We give you the math stats knowledge with kind of the 100 series and 101A, 101B, and then this hacking skills, machine learning stuff comes in with the 102 series and 101C. And this part, the substantive expertise, is basically doing this stuff without being aware of the data itself, okay? Is not a recommended thing, okay? And so you should be familiar with whatever field that you're doing the data analysis on, okay? So if you're going to do data analysis on video games, you should be somebody who's familiar with video games, okay? And if you're going to do something on sports, so like if you want to do baseball, like analyze baseball data, you should be familiar with baseball, right? And if you're not familiar with baseball, then seeing these numbers, you're not going to have a way to check to make sure if your resulting models even make sense. Okay, so that's an important part. Obviously, there's too many fields out there that you can apply statistics to, so we don't even try to give you that. Okay, that's up to you to kind of pursue and go after. Okay. Let's see, 10:25. All right, we'll see how far we get in today's lecture, and then I'll cut it and push the rest onto Wednesday. But this is our first lecture, lecture 1.1, and we're going to just start off with kind of asking, what is machine learning? Okay, and Wikipedia says machine learning is the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without using explicit instructions, relying on patterns and inference instead. I copied that from Wikipedia like yesterday, and so if somebody modified it, then it might be different. But anyway, that's what it says. This is kind of my take from this, is that we're going to fit models to data. Okay, we've got statistical models. We're going to fit it to data. And then, and here it says to effectively perform a task without using explicit instructions. And I'm not quite sure what they mean by explicit instructions, because even if you have the computer do it, you're giving them an algorithm, which in my opinion is explicit instructions, right? So I'm not quite sure what they mean here, but basically, my interpretation and what I believe kind of machine learning, a lot of it is that, you as a person, as a researcher or the, data analyst, data scientist, whatever you want to call yourself, you're going to have to make decisions anyway, okay? But as far as specifying the model and what kind of model to use and all of this, hyperparameters and stuff, but a lot of the decisions that you end up getting for the model are guided by the data and the algorithms we use, okay? So a lot of decisions on, like which variables to use, a lot of that, when we do machine learning, which variables we use will be guided by the data, okay? Whereas in 101A, when you did linear regression, I imagine as far as variable selection, you probably had like forward stepwise variable selection, backward stepwise variable selection. You looked at things like your AIC, BIC, and I don't know, whatever else, log likelihood ratios and all of this. And these were how you decided ultimately, I want to include these 6 variables, or maybe I can only get away with only using 3 variables and still get a pretty good model and stuff like that. And there was a lot of, you had to think about the data, or you should have done some thinking about the data regarding which variables to include and which ones not to use. And in machine learning, a lot of that thinking and decision making stuff is guided by the algorithms themselves, and you do a little bit less of that, but obviously you still have to make some choices here. Okay, I made this thing because I remember when I started in grad school. I don't know if you know my background, but I did not study statistics as an undergraduate student. And so I got to grad school, and they're all talking about statistical models. And I was like, I don't even know what a statistical model is. And so this is how I felt like the first half year of grad school. And eventually I think I figured out what a model is. But I don't know if you guys are in this situation or not. This was definitely how I felt, for the first half year, maybe even the first year of grad school, where I was just struggling. But anyway, so this is what I say a model is. Okay, we can think of it as a simplified representation of something complex, right? So this is a model of a airplane, F-16 airplane, which is very complicated, and this is just something to kind of represent it. Yet it gives us a good picture of what an airplane is, okay? And so likewise, when we talk about a statistical model, we're talking about a simplified representation, okay? Not the real thing, okay? It's just a representation of something that's probably very complex that exists in the real world, okay? Something that generates data, okay? So in the real world, there's something that goes on that generates data. And when we make a statistical model, we want to create kind of this approximate representation that will also kind of generate data, at least something that looks kind of like the real world data, right? And so yeah, it says the process that generates the data in the real world is complicated. There's lots of things that determine the outcome, and depending, like if you wanted to model, or if you wanted, let's say you're Amazon, right? And you want to know who's going to purchase this book or purchase this product or whatever it is, right? They've got like 1 billion, I don't know how many things they sell, but lots of things, and you want to know who's going to buy this. There's a lot of factors that go into whether, let's say we want to know who's going to buy this textbook, right? And you as a student, you're going to say like, well, how much does it cost? And do I actually need to buy it? Can I get it from the library? Do I feel like searching online for an unauthorized resource, or I don't know, whatever, right? Maybe just the mood that you were feeling. Maybe the day before you talked to somebody and they were talking about how They want to live honestly and not, I don't know, whatever, right? And all of these things factor into your decision-making process, right? It's complicated, and I don't know, we can get philosophical on whether we actually have free will or not, and whether the decisions we make and the words coming out of our mouth are actually my own or just the result of synapses firing in my brain of which I have no control over. But we can't model all of that, okay? It's too complicated. So we're just going to make a simplified version of this thing, right? And we're just going to pick a subset of variables, just a few things that are going to be important, maybe the cost of the book and I don't know, whatever else, right? And of course, to account for everything else that we didn't include, we throw in an error term. And usually that error term is represented by a random process, like Gaussian noise, or I don't know, some other kind of random, what do you call it? Random distribution. And that's why, you know, there's a strong overlap between probability and statistics. And so that's what we're going to try to do, okay? There's a quote, all models are wrong, but some are useful, in that every single model that we have is not going to be the real thing. It's just an approximation, so it's never 100% correct. But the models themselves are useful in that we can use them to make predictions, or we can use the models to explore relationships between variables. And this was this use, probably, of exploring the relationships between variables, that was a very important thing in your regression, your 101A class, I'm imagining. And you picked out the variables, you know, ultimately, which are the things that determine like the cost of a house. Is it the number of bedrooms or the neighborhood you're located in, or maybe those are the two that are most important, and things like that, okay? And sometimes we care about one of these goals more than the other, okay? And that will inform which kind of model we're going to use, okay? Do we want the model that gives us good interpretation? Do we want the model that gives better predictions, okay? And they don't necessarily have to be in opposition to each other either, okay? All right, so in the textbook, there's an example that we start off with for linear regression, and we're looking at the men's 100-meter race in the Olympics, okay? That's like the one that Usain Bolt and, you know, they run really fast, and there's a bunch of things, right? A bunch of factors that go into determining what the winning time is at the Olympics, okay? And all we're going to do is we're going to try to make a simple model, okay? And so this is what the data look like, okay? We read in the CSV, and it plots like this. And so I guess the first Olympics was, at least the modern Olympics, 1896. And then, and it looks like times have gotten better and better and better pretty much every year, right? Not every year, but every 4 years, every Olympics event. Over time, there's definitely a downward trend, okay? Can't be sustained forever, but you know, what we're going to do is we're going to say we're going to fit a linear model, right? This is already stuff you know, but basically the linear model says that, well, it sure looks like the race times have gotten faster as time has gone on, and so we are going to fit a linear model, which says that if we know the year in which the Olympics were held, we can predict the winning race time. And linear means that the amount we adjust is going to remain constant throughout the data set. Okay, so if our prediction improves by 0.05 seconds from say 1920 to 1924 or whatever, okay, if that's the kind of the overall trend, then we're going to make the same kind of adjustment of 0.05 seconds, you know, 80 years later from 2000 to 2004, okay? So linear means same adjustment throughout the data set, and if it's nonlinear, then it means it's going to depend on how big the values are, okay? And so when you fit the linear model, you're going to fit a straight line, which means you're going to have a slope and you're going to have an intercept, right? And so fitting the model fitting the model is the process of estimating those parameters. In this case, we have two parameters to estimate, slope and intercept, and fitting is just picking which parameters, what values we should use for those parameters, okay? And so we want to estimate, we want it so that the resulting model does the best job of fitting the data, okay? Whatever that means, right? And so the idea of how we define best is going to be very important, okay? So, so for linear regression, okay, often we might call it ordinary least squares regression. Ordinary least squares describes how we define what best is, okay? Best means we want to minimize the squares of the residuals. We want to minimize the squares of the residuals, right? And residuals, the difference between the actual value and the predicted value, okay? So if the actual data point is y sub I and the model predicts y hat sub I, this y minus y hat is your prediction, and then you square that, and then you add that up, okay? And so I'm assuming this is all review. You guys all know this from 101A. This is your residual sum of squares, your RSS, and this, because this is the thing that we are trying to minimize, this is what we call the objective function, okay? The objective, it's your goal, your objective is trying to do something with this function, and in this case, it's a function that we want to minimize, so it's also known as a loss function, because you want to minimize your losses, also called a cost function, because you want to minimize your costs, okay? So, so this is what we call the objective function, and this, I'm hoping for least squares regression, this is something that's very familiar, okay? We're trying to minimize the squares of the residuals, where the residuals, the difference between the actual and the predicted value. And so when we look at machine learning models, okay, including linear regression, we define our models, or we set up our models in such a way that there's one function that we're trying to maximize or minimize, okay? And we call that the objective function, okay? And we're going to start here because I'm hoping this is all familiar to you, and so I can start introducing some of these machine learning concepts, and we can understand all of this. Okay. I'm going to use the textbook notation, okay, just so that when you follow along in your textbook and it uses all of these letters and stuff, my notes will kind of match what they have, okay? And so in the textbook, rather than calling your observed data y sub I or whatever, they call it t sub n for whatever reason, okay? So the values that we observe are t sub n, and then instead of using y hat for the predicted values, they just run the function. Okay, they just insert the function, and they say because it's a function using the parameters w0 and w1, we're going to call it, you know, the predicted value by the model is going to be f of x sub n, you know, with parameters w0 and w1. Okay, and so if we and then textbook, rather than using the total squares of the residuals, it uses the average or the mean squared error, okay? The mean squared error is just going to be this divided by n, okay? And so, so our loss function, the loss function which we use this fancy L for, is written this way, okay? So t sub n, the actual, minus what the model predicts, okay? And we take that quantity and we square it, we add them up and divide by n. Is that good? Okay, so we're just rewriting what I'm hoping is familiar to also something familiar, just changing up the letters. Okay, so this is now mean squared error. This is our loss function, and we want to minimize the mean squared error, okay, for linear regression. Okay, side note, a lot of times you'll also see root mean squared error, which is just the square root of that thing, okay? And so for linear regression, the parameters that optimize the residual sum of squares is going to be the same parameters that optimize mean squared error and root mean squared error, okay? So no biggie there. Okay, so the linear model, we've got two parameters, the intercept and the slope, and when we plug those in, okay, we have W0 plus W1 x sub n, and when we plug this in, our loss function becomes this, okay? The loss becomes 1 over big N, and then now we're just plugging in T sub n minus W0 plus W1 x sub n quantity squared, okay? So that's what it looks like when we just expand out this function, what the model says. And to solve for the best arguments, W0 hat and W1 hat, those are going to be the values that minimize, this function, right? So all we say is we're going to just find the arguments that minimize our loss function, okay? And the results, okay? The values that minimize the loss function, the values of W0 and W1 that minimize it will be our W0 hat and W1 hat, okay? Because at this point in our study, X and T, the input and output, are fixed, okay? These are fixed values that exist in our data, and now we are trying to find the best slope and the best intercept, okay, that minimize the loss function. All right, so I'm going to start by taking this, and then you square it and you expand it out, okay? So this is just, I don't know, algebra, right? And then so we expand it out, and then how do we solve for W0 and W1? Okay, so we're going to find the partial derivatives with respect to W0 and W1. We set them equal to 0. We solve for W0 and we solve for W1, okay? And so I imagine this is stuff you had to do back in like 32A, your multivariable calculus and stuff, to find minimums and maximums of multivariate functions. Okay, and I'm gonna kind of if you just skip ahead and not, so the partials, you don't have to write all of this down. It's already, this was like such a pain to like typeset in LaTeX, but I did it for you guys, so your notes are complete, okay? And so anyway, your partial derivative looks like this for W1, and your partial derivative for W0 looks like this, okay? And what we do is we solve this equal to 0. We set this equal to 0, and we set this equal to 0. Now you have two equations and two unknowns, and you go through a bunch of stuff, and you're going to find the W0 hat and the W1 hat, okay? And I say you can check the textbook for the completed work. I feel like I can get away with just saying, I hope that makes sense, and as far as the process goes. And you can solve for basically the estimators W0 and W1 that will minimize the mean squared error, okay? And and it's going to result in what we've always known, right? It's going to result in W1 being correlation R times the standard deviation of Y over the standard deviation of X, and W0 being your Y bar minus W1 times X bar and things like that. Okay, what we are going to do next, and I think we're going to have to save this for Wednesday, is we're going to change all of this into matrix notation and use linear algebra, okay? So if we look at this, hang on, I'm not done yet, okay? I've got a few more minutes, all right? If we look at this, there's this summation term, because we've got a ton of observations, right? You've got n observations. You're going to have this summation term, which can be annoying to deal with. And so by being able to express things in matrix form, it simplifies our lives, okay? In the beginning, when you have to do things in linear algebra, it hurts your brain, and you're like, oh, I didn't do great in linear algebra or whatever. But it's kind of one of those things where it's like, you just got to trust me on this. It's going to be better dealing with matrices and working in linear algebra, okay? And it will allow us to avoid dealing with the summations, okay? Because when you do like a dot product in linear algebra, the summation is implicit in the dot product, okay? And so, or you do matrix multiplication, summation is there, and it's implicit, okay? If it's been a while since you've taken linear algebra, or if you just haven't seen these videos before, which are like the best videos on linear algebra I've ever seen, and I'm not even kidding, you got to watch this this playlist, okay? It's by this guy who calls himself 3 Blue 1 Brown. They're on YouTube. Each video is about 10 minutes long. They've got classical music playing, and they really are the best. Okay, so anyway, that's what we will do on Wednesday. We will revisit this problem in matrix notation. All right, we'll see you guys. We'll see you guys then.